Hello, and welcome to part 1 of a larger project. Let's make Worms.
I'm sure most of you are familiar with Worms. It's a side-scrolling game where you have teams of worms that battle each other with trajectory-based weaponry. The landscape in Worms is randomly generated each time, and we can see we've got here the green landscape versus the blue sky, or non-landscape. And I can press the M key to randomly generate terrains as necessary using the Perlin noise function. And as this is a multi-part video, we won't be looking at the entirety of Worms in this intro demonstration. Instead, I'm going to show you what we're going to achieve today, which is the addition of units, which you can see have collision detection and response with the terrain. And we'll also add arbitrary explosions, so I can click somewhere and it causes an explosion, and also damages the terrain with a crater. And if you cause an explosion near a unit, it blasts them around the screen. Very nice. And the final part we'll be adding is sequences and events. So here we're creating a weapon object which when collides sort of combines all three things together.
Now, even though I'm splitting this project up across several videos, there's still quite a lot to get through, so I'm going to be going through at a slightly quicker pace than normal. After all, a lot of the techniques we see in this video are based upon techniques I've already talked about in previous videos. So it's all coming together to form one nice project at the end of the year.
And of course, I'm going to be using the OneLoneCoder console game engine. And I've already taken the liberty of just deriving a quick base class from this. It does nothing other than implement the onUserCreate and onUserUpdate functions. And in my int main, I'm constructing a console which is 256 characters wide by 160 characters tall, and each character is going to be 6 by 6 pixels.
And just a quick interruption to say a big thank you to all the people that have joined the Discord server. There's almost 100 lone coders out there now. And if you're interested in joining in and getting involved in the chat, there's quite a lot of talent on that chat server. Then I suggest you look at the links below for an invite to the Discord server.
Now, it may be boring, but it is very important that with any big project you form a plan before starting. And Worms is no different. I know that I've got randomly generated terrains. And these are randomly generated to the pixel level. And given that Worms is a game about accuracy, I think it's important that we have pixel level collisions. So that's the first requirement. Worms is a game all about trajectories. So assuming you've got a little unit here and he can fire his weapon across the terrain. The terrain gets altered and then causes multiple more trajectories for debris. And possibly other units. But when debris lands on the surface, it doesn't just immediately come to a stop. It carries on bouncing a little bit. So we know we're going to need a very simple physics engine. Well, both of these are hard. Let's do what we can to simplify them, yet keep them working in a way which is suitable for gameplay. And the first approximation I'm going to make is that even though sprites are traditionally rectangular, I'm going to assume that all objects in my physics engine are circular. And so I've got a unit object, a debris object, and even though we didn't see it, I've got a missile object. Now, in a lot of games, when you want to do collisions with maps, you do things like make assumptions that the map is in fact created out of straight lines, and so then doing circular with straight line collisions is quite simple, or circular with polygon collisions is quite a simple thing to do. But that's not how the original Worms works at all, and we want to try and retain the look and feel of that game. So we will have to do a per pixel collision detection routine for a circle. And although we won't do it in this video, circle-circle collisions are actually quite easy to do, and may be useful, for example, if we want units to knock other units.
As you can see, there's quite a lot to do, but I'm going to let object-oriented programming and polymorphism help us out.
Everything that can move in my game is going to be derived from a class which represents a physics object, and this class will be abstract, but it'll contain useful information such as position, velocity, acceleration, and a flag that represents whether it is moving or not, a stability flag. I'm also going to define a pure virtual method which makes this object abstract, draw, which will be used by subclasses to draw themselves on the screen. The missile and debris subclasses are going to be represented by wireframe objects. using the code that we made for the Code It Yourself Asteroids video. And this is because I want the missile and debris to rotate, to represent the angle it's travelling in. The third subclass, Unit, or Worm, is going to be represented by a sprite. I don't need these to rotate, and so each subclass will implement its own version of the draw function using the correct technique required. This is a simple yet powerful use of polymorphism, because I don't need to maintain any object management code. In fact, all I'm going to do is have a list of the objects, which I can then iterate through, calling the draw routines and updating the physics.
But let's start at the beginning. Let's create and draw the terrain.
As the terrain needs to be accurate at a per pixel level, I'm just simply going to create a map. And this map is just a two-dimensional array, in this case 1024 by 512 pixels, of unsigned chars.
At the moment, the map is just going to be filled with zeros and ones. It's going to be 1 wherever there is land and 0 wherever there isn't land. You might think I could just use booleans for this. However, later on I might want to add different types of land or different colours to give it some texture.
And so in the onUserCreate function, I'm just going to allocate the memory for that two-dimensional array, and then use the memset command to clear it all to 0. Why not? I'm going to separate out the map generation to a createMap function, because I still want the ability to scroll through maps and interrogate them and find ones that I like. Now I also know that my maps are going to require Perlin noise, so I'm just going to cut and paste absolutely character for character from the Perlin noise video, the Perlin noise 1D function, which, just as a reminder, takes account of the number of elements in the array, a seed array full of noise, the number of octaves we're interested in generating, and the bias, which was how do the octaves relate to each other. And of course we have an output variable too. I'm not going to go into what Perlin noise is, please click on the link above to find out. But to use the Perlin noise function, we need to prepare some data. We need a one-dimensional array which represents the surface that is generated, and this array will be filled with heights. We also need a second array which is going to be filled with our noise values. I'm just going to use the rand function to generate some noise. I'm going to hack the Perlin noise just a little bit by setting the first value to 0.5. Because my Perlin noise operates between 0 and 1, this means that my first element will be halfway up. It also means that the last element in the array will be halfway up because the Perlin noise samples at a fixed interval. And this means that my terrain will both start and end halfway up the screen.
And this just adds a little bit of consistency to the terrain generation. Otherwise we could have terrains which start at the very top of the screen and offer no place for the players to fight. Or they could operate at the very bottom of the screen and actually have little tiny islands and bubbles with no land for the worms to walk on.
Now we can call the Perlin noise 1D function. Now don't forget that the fSurface variable is one-dimensional, but I've got a two-dimensional bit map representing the terrain. So instead, what I need to do now is scroll through all of the elements in my map and compare them to the heights in the surface array. Now all of my arrays assume that top left is 0, 0. And given that land is usually below the sky, I'm therefore checking that if the current pixel in the map is greater than the corresponding pixel in the surface map, set it to land, or else leave it as sky. And that's all that's required. I'm just going to tidy up those two dynamically allocated arrays. Just so that there's something there at the start, I'm going to call the createMap function after I've created the map array in my onUserCreate function. The onUserUpdate function for this project is going to get quite complicated, and occasionally we're going to have to throw in code just for debugging and checking, and this is one of those cases. I'm going to make it that whenever the user releases the M key, it's going to call the createMap function again, so I can create new maps whenever I want. Drawing the landscape terrain is quite simple. I just iterate through all of the pixels on the screen, given by screen width and screen height, find the location in the map, and choose whether to draw it as sky or as terrain.
But we're missing one important thing here.
The size of my terrain map, 1024 by 512, is much larger than the size of my console.
So I can't fit the whole map on my console display. I'm going to have to create a camera and some camera control code to choose which part of the map we display on the screen.
I'm going to add two more variables, camera position X and camera position Y, and they're going to be floating point. I'd like to be able to control the camera by moving the mouse cursor to the edge of the console. And when I do, the map scrolls in that particular direction at this particular speed. And for this project you'll see me using lots of hard-coded numbers, which I've already decided are the best value.
After all, it would be quite a frustrating and boring video watching me randomly try numbers to see if they work, wouldn't it?
By using the console variables for mouse, I can check, is the mouse within, say, for example on the left hand side, 5 pixels in from the edge? And if it is, I want to update my camera's X position using f-elapsed time to make it smooth. In fact, I'm going to do this for all 4 edges of the console. But this leads to a rather dangerous situation that the camera could exist outside of the map space, which means we'd be drawing random elements of memory and all sorts of chaos would ensue. So I'm going to maintain control over the camera by clamping it to the edges of the map. So now when we draw our map in the draw landscape routine, I'm going to offset it by our camera positions. I'm going to convert them to integer, of course. And we're using the now very established technique of y multiplied by width plus x to work out where we are in the 2D array. I think we're ready to take a look now. So the console has started up and we're in the sky, so if I move the cursor down, yep, that's good. It scrolls down the screen and up the screen and across the screen in both directions. And we can find all the way to the edge and we see it stops automatically, so we're not going to be looking at parts of the terrain which we shouldn't be able to see. Very nice. And if I press the M key, I'm not moving the mouse, but I'm generating different terrains each time. What we should notice, though, is that the terrains all start from the same point. And they do. And that's because we fixed the first value to 0.5. Of course, I could fix it to, say, 0.25, and it would be higher up or lower down.
We've now created a two-dimensional pixel-level map that represents the terrain. In fact, it represents a very large terrain, and we can make it larger by playing with the numbers. And you can look at the Perlin noise video that I've done earlier this year to look at the parameters for generating Perlin noise to generate different types of terrain. I know that in original Worms the terrains can have overhangs and floating islands in the sky and gaps. And these are all achievable too, but they probably did start with an element of Perlin noise somewhere. But to keep this video moving, I'm not going to do that. We're just going to have a single terrain.
Right, let's get stuck into the fun stuff now and create our physics engine. We're going to start by defining a base class called CPhysicsObject. And I'm going to have some directly accessible properties just to annoy people that represent the position, the velocity and the acceleration. They're all going to be in floating point. In fact, the whole physics engine is going to be a floating point physics engine. I'm also going to add a default constructor which allows us to set the position. There were 2 other variables we're interested in: a radius, which represents the collision boundary of the object, and a flag that represents whether the object is stable.
Stability is quite an important thing to know in a physics engine. Firstly, if an object is stable, we don't need to perform more computation on it. If it's not moving, we don't need to do collision checks, for example. But in our game it's also quite important too. Let's say the worm has just been blown around on the terrain, and he's finished bouncing around. How do we know when to pass control on to the next worm?
In the plan we said that CPhysicsObject was going to be abstract because it defines a virtually pure draw method. This draw method takes some parameters. The first being a pointer to the console game engine. And this is quite important because my physics object sits outside of any of my console game engine stuff. Yet I do want to exploit some of the drawing routines, such as drawing wireframe models and sprites. So this is a way of getting the instance of the game engine into the object code. I've also got 2 other arguments, offset x and offset y. As you can probably guess, these are going to be related to the camera, and not the object's position in the world space. To help debug the physics engine, I'm going to create a dummy object, which inherits from the CPhysicsObject. I'm going to call it CDummy. I'll need to create a constructor for my dummy object, which just passes through the x and y position in world space. And because my base class is abstract, I need to implement the draw method somewhere. Now I'm going to add something which I'm sure is going to cause me no end of bother in the YouTube comments and on the Discord server. I'm going to add a private static variable to a vector of pairs of floats. Now this vector of pairs of floats is exactly the same data type we used in the Code It Yourself Asteroids video. In fact, this is how we're going to store a wireframe model. And I'm making it static because I might create 100 of these dummy objects, but I don't want to keep recreating and allocating resources to store the same model for each object. So I want one model to be shared across all objects of the same class. And it's going to get a little more complicated because I need to initialize this variable, and I'm going to use a factory function to do it. So when the program comes around to defining exactly what VecModel is for the CDummy class, it calls the defineDummy function. And the defineDummy function produces a list of points in a circle. And in fact, it's a unit circle, because we know that the draw wireframe functions will scale for us. But this approach is nice, because I only need to do this once, regardless of how many dummy objects are going to be floating around in my world. And so to draw the object, I'm just going to call the draw wireframe model, which is part of the OneLoneCoder console game engine class, and that's why we've passed it in as a pointer. And so the parameters are draw the model data, which we've already created, it's part of that static variable, the x and y locations, which are of course the local x and y in world space of the object, but offset by the camera, which we've also passed into this function. I also then need to choose the angle at which we rotate the object, because it's wireframe, and to do this I can use the atan2f function of the velocity components. And I also want to scale the object size, and I'm going to use the radius variable to do this, so that we can see the bounding radius for this object. And finally, I'm going to use white characters to draw.
And for the OneLoneCoder channel, this is some pretty advanced C++ stuff going on here.
Let's now start adding the objects into the game, and so I'm going to create a list of CPhysics object pointers. And there's a reason that they're pointers. If they're not pointers, and because the CPhysics object is abstract, I'll get a compile time error. I can highlight down here, CPhysics object cannot instantiate abstract class.
And this is what allows us to add things to this list which aren't necessarily directly CPhysics objects. They are subclasses of it, so we can add worms and units, debris and dummy objects to this list, and they'll all get treated in the same way.
But there is a little caveat to this, which we'll see later. I want to see if our drawing routine works, and generally does our object hierarchy work. So I'm going to make it that whenever the user presses the middle mouse button, which is 2 in my setup, I'm going to add a dummy object to the list. So I've allocated memory for the new dummy object, and I've set its starting position to be wherever the mouse has been clicked. But don't forget to include we're offset into the world, and the mouse position is relative to the console position. And now we get to exploit the power of polymorphism, because after we've drawn the landscape, we want to draw all the objects. And this is very simple indeed. In fact, it's just this. We just scroll through the list and we call its draw routines. And this is really nice because it doesn't really matter what object it is, it'll just sort itself out. So let's take a look. So I'll just move it down so we can find some terrain, and if I click on the screen with the middle mouse button, I can place an object, and it's crudely circular. What you'll see is I've actually also added a line from the middle of the circle to the radius, and this was defined as part of the object in that static definition, and we can use this line to say what angle of rotation has been applied to the wireframe object. In this case, we haven't even looked at velocity yet, so they're all pointing in the same direction, which is just some default startup direction. And of course, we've got no collision, so I can put these things all over the screen. If I move the camera, they move relative to the terrain. We can use a similar iteration to update all of the physics. And in the asteroids and the Flappy Bird video, we can look at how we do the physics very simply for 2D objects. The first thing we might want to do is apply any additional forces to the acceleration. And the velocity is just the integration of acceleration with respect to f elapsed time. And the position is just the integration of velocity with respect to f elapsed time. You'll notice, however, I'm not doing it directly to the position members of the object. Instead, I'm calculating a potential x and y, and that's because we want to test for a collision. And if a collision has occurred, I don't want it to move to that location because it means the object will be within the object it has collided with. So we're just going to see if things carried on as they were, where is it going to be? Once I've applied the forces, I'm going to reset the accelerations to 0, and I'm going to set the stability flag to false, because the object is clearly not stable. It's in a state of flux, it's moved. But since we're not doing collision detection just yet, let's update the object's position with its potential x and y coordinates. Let's take a look. I'm going to find the terrain, I'm going to place an object, and we can see it's pointing down, and it's falling down, but it's accelerating as it's falling down due to the effects of gravity. Let's put a whole bunch of objects in, and they all behave independently. Very nice, although a bit slow.
Physics engines and graphics engines rarely coexist at the same speed. And proper physics engines, not like this one, really don't like having changes in time step. Now I know that with the OneLoneCoder console game engine, drawing to the screen is actually the slowest part, and that the physics at this level that we're calculating them at anyway will really take up no CPUs at all. So for every frame of graphics update, I'm going to do 10 frames of physics update.
Which is simply a case of wrapping up the update physics loop in a second loop. And so if I run it now, find the terrain again, scroll it down, you see the objects fall at a slightly faster pace because there's 10 times more updates happening. Let's consider how we're going to handle the collision detection. The first thing we need to know is, has a collision actually happened? And because we represent all of our objects as circles, it doesn't really matter what the object looks like, we can use the same technique to see if it's interacting with the terrain. I think the first optimization we can make is we don't need to check all of the points that lie on the circle. We only need to check those that lie within a semicircle rotated to the direction that the object is moving. So this red arrow represents the velocity vector. If we take 90-degree points, we only need to check along this part of the circle. These points we don't care about because they can't possibly be colliding with anything. The number of points along the circle's edge needs to be sufficient that at least one point is residing in 1 pixel of world space. Now in my simple demonstration, I know that I can just simply choose a theta value sufficiently small enough that it will be, because none of my radiuses are very large. But a sensible approach would be to choose a theta value based on the radius that ensures that the pixel difference between the 2 points is always less than 1.
And we need to do this because it's going to happen where we've got 1 pixel floating around in space, and that 1 pixel shouldn't be ignored.
So it's not sufficient, for example, where I'm putting these big green crosses, to just have a handful of detection points, because it's very easy for a pixel to fit in between the gaps. However, I'm doing nothing more clever than just choosing a small theta value. Once the object has been moved, we've calculated its potential new location, and we can then compare the red dots along the circumference with the world map to see if collisions have occurred. And we can see, yes, there's a collision here, 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 and here. If we create vectors to these positive collision points, and sum them all and invert them, we end up with a response vector. And this vector approximates the direction that the object needs to move to escape being in collision. But it also has one bonus feature. It also approximates the surface of pixels that have been collided with. In fact, we can assume that the response vector is indeed normal to the tangent of the terrain surface at this point of collision. And so once we've discovered the normal to the collision point, and we know the trajectory of the object coming in, we can calculate a reflection, very simply, which is just incident and reflection mathematics. We'll see that in a bit. Let's add in collision detection. And this is just collision with the map, not collision between objects. And the first item I'm going to need is the actual angle in radians derived from the velocity vector, as we saw for the rotation of the wireframe objects before. I'm also going to create an x and y component of my response vector. Once I know this angle, I'm going to create a for loop which iterates from one side of the semicircle to the other, at, in this case, a fixed step size. But as I've just been describing, you could probably do something more clever here to ensure that all of your points are within a unit distance from each other. Using sine and cosine, I can take the radius of the current object plus the angle of the point being tested and the potential new location to work out where in the world map I'm testing for a collision. And I'm going to call this testpos x and testpos y. So these points are the points that lie along the semicircle that's been rotated to the direction the object is moving. I'm going to be reading from memory, so I want to make sure I've got control over these points. I'm going to clamp them to the size of the map. And it's just simply a case of reading that location from the 2D map array. And I'm going to assume that anything that isn't 0, so anything that's not sky, is terrain, so that's a positive collision. And so I'll sum that point into my response vector. I'm going to just create an additional variable called collision, and I'm going to set that to true here when a collision has occurred, simply because I don't need to do anything further if a collision hasn't occurred. So if a collision has occurred, I want to respond to it, else I'm going to allow it to use the new potential positions.
Now, in other physics engines, collision resolution is a really fundamental part, and it has to be very accurate, and I'm not striving for accuracy here. It's a game of worms after all. I know that in my physics engine, objects aren't going to be stacking on top of each other and resting on each other and continuously interacting with each other, so I just want to emulate the effect. I'll break the rules of physics a little bit to make things simpler for me.
For example, when a collision occurs, I'm going to set my object to stable, and I don't allow it to update its position. This means it will be the case that the object technically has collided with thin air. Only its potential location for collision actually results in a collision, but I don't want the objects to overlap with the terrain. I'm going to use my response vector as the normal to the tangent of the terrain, and use this in a reflection calculation so I can get a reasonably accurate bounce of the object. The first thing I'm going to do for convenience is calculate the magnitude of my velocity and response vectors. I'm going to be using these several times. The mathematics behind a reflection vector is quite well known. Just find it on the internet. It's actually quite a simple equation. I'm just going to use the code directly. So the first thing I'm going to do is create the dot product between my object's velocity vector and the response vector, but the response vector has been normalized. And I calculate my object's new velocity vector, which is the reflection vector, based on the reflection equation. Let's take a look. So I find a bit of terrain, and I drop an object on it, and it bounces, and it bounces, and it bounces, and it keeps bouncing, and off it goes. It's on its way. Very nice. Oh, and it hits an alternative edge, and now it's bouncing all the way back. Very nice. In fact, let's add a whole bunch. Let's get them going all over the place. And you can see some are just bouncing directly up and down, and that's because there's not enough information in the area that they're hitting to actually give them any curvature. It's just unlucky that they're finding the flats here. And this is exactly what I'm saying. This is just an approximation to a physics engine. It's good enough for a game of worms. But it would be quite an exciting game of worms because nothing is ever settling. I'm going to add another variable to our physics object, which emulates energy loss, or friction in this case. And all I'm doing is taking the reflection vector and multiplying it by this coefficient. So it'll be a value between 0 and 1. Let's throw that in, and we'll set it to 0.8 to begin with, just as a default value. Now when an object collides, it loses some of its energy, potentially. You see it comes to rest. The bounces aren't as high each time. And also, now that the objects are bouncing around, you can see that the wire mesh is being rotated to suit the velocity direction. And it would seem in this video, it depends on the frame rate of the YouTube video, that 2 of these objects have become stable and 2 of them haven't. And this is because of the asymptotic nature of how I'm updating the velocity vectors. At some point I just need to simply say, look, there's not enough movement to actually count as movement. So I'm going to do that deliberately by looking at the magnitude of the object's velocity vector and seeing if that's less than a small enough amount. And if it is, I'm forcing it to true.
Now we've got a rudimentary physics engine, let's create some debris objects and some explosions.
The debris object is going to look very similar to the dummy object. So I'm just basically cutting and pasting the same thing. I've defined the class, and I've also created a static definition for the model. And in this case, the model is just a square, a wireframe square. And when the object draws its wireframe, it uses the dark green pixels to do it. So in this way, it's different to the regular dummy object. What I will add though, is that when debris is created, its velocity vectors are assigned a random vector to make it shoot off in a random direction. And we'll test this by using the mouse button to spawn debris. And this is where we see all of the effort that we put into the polymorphic object hierarchy pay off. Because all I need to do is add, say, 20 new debris objects to the list. And the position I'm going to give them is the mouse coordinates in screen space translated into world space. I don't need to make any other alterations, because the objects will draw themselves and the physics engine will look after them. So let's find the terrain again, and I'll click the mouse, and you can see it spawns a whole bunch of objects which just bounce around until they all run out of energy. Keep clicking and clicking and clicking. Loads of objects, all being handled by the physics engine. Okay, the frame rate's taking a bit of a hit. The nice thing is, they're all gathering in the pockets on the terrain. But there's a problem here. We can't just accumulate objects until the end of the game. The debris needs to disappear after a while. And so what I'm going to do is limit the number of times it can bounce. And once it hits this limit, it's going to flag itself for erasing. I think limiting the number of bounces an object can do before it dies is quite fundamental. For example, a missile won't bounce at all, but debris could bounce several times. However, a grenade may bounce. So I'm going to add some variables. Bounce before death is the number of times the object can bounce before we set its dead flag to true. And if this is set to a -1, the object can just carry on bouncing. We know that the object must be bouncing if a collision has occurred, so we'll put our bounce detection in this. If the object has a positive bounce before death count, then we'll decrement it 1 and set the flag if it's set equal to 0. But this leaves us with a bit of a memory problem. Objects which are dead need to be erased, and so we should remove objects which have their dead flag set when we're processing them during the physics update. The nice thing about lists is they have the remove if function, which takes a very small lambda function as a parameter, and so it'll only remove the objects where the object contains a bdead flag which is set to true. However, this function doesn't delete the object, it just removes it from the list, and at this point we've lost all control over our pointer.
We've actively created a memory leak. This is bad. So what can we do about it? I could create a system of alternate lists and loops and checks for validity and try and iterate through things and erase them myself, or I can use some C++ constructs to do the job for me. And I will.
Instead of just storing the pointer directly in our list, I'm going to use a smart pointer. In fact, I'm going to use a unique pointer, which points to a physics object. And the nice thing about a unique pointer is that whenever it goes out of scope, it calls delete on the object that it's pointing to. But we have to make a few changes to how we add things to the list. We can no longer just push back directly the pointer to the object that we need to push back a unique pointer to the object. And the same applies to our dummy pointer. We'll just also modify the remove if function in the list to accept a unique pointer instead. And the nice thing now is that as soon as the unique pointer goes out of scope, it's deleted. So as soon as it is removed from the container, as long as it has no owner, the delete function is called on our physics object. And this means we don't leak any memory. We need to make one more change to our C debris object, which is to add the number of bounces it can do before it dies. I'm going to say it's 5. Let's take a look. Let's find a part of the terrain, we'll launch an explosion, and we can see the objects disappear after they've bounced 5 times. Let's create lots of explosions, lots of objects, really hammer the frame rate, but eventually they all disappear and things go back to normal.
Explosions seem to be one of the fun elements of this game, and I think we're going to need quite a lot of them, particularly when grenades explode, sub-grenades for example, and there's explosions all over the map. So I'm going to create a function which handles just explosions.
And I'm going to call it boom, and it takes a coordinate which is x and y in world space and has a radius which is the area of effect of that explosion. So we know that one of the things our boom function is going to do is spawn lots of debris. So it's just going to do what we did before on the mouse click, it's going to iterate through up to a certain number, just adding debris objects to our list of objects to process. I think probably the radius is a good indication of how much debris we should create. So for small explosions which have small radii, we generate few debris objects, whereas big explosions, we generate lots. But I also want to affect the other objects that are nearby. I want to knock them about a bit. So I'm going to have to iterate through all of the other objects to see if they are near to where the explosion is happening. And this is a very simple calculation, it's just Pythagoras' theorem. I take the explosion location, the object location, and work out the distance between them. And if the distance is less than the explosion's radius, then the object gets its velocity updated by the distance between the two objects. So an object which is very close to the explosion gets a velocity boost larger than an object which is slightly further away. I'm also going to set the stable flag to false, because, it's just been exploded. I will make one little security check here, which is to make sure we don't have a divide by 0, because then potentially we're setting our object's velocity to infinity, and it will be blasted out of space and time.
And this may confuse the player.
So instead of launching the debris directly now on a mouse click, I'm just going to call the boom function. And I'm going to borrow the camera position variables from before. And we'll say that a little explosion has a radius of 10. So let's take a look and see if it interferes with other objects. Let's first of all place some units. There we go. and I'm clicking, it's causing an explosion, that's good, and if I click in this cluster of objects, we can see they get knocked about. And if I try and launch an explosion far away from the objects, it gets affected very little, but if I launch it in the middle of the objects, it gets affected a great deal, proportional to the size of the explosion. But we can see we're not doing any damage to the terrain. Given that our terrain map is simply a bitmapped image, I'm going to use the circle drawing routine to erase parts of it, i.e. I'm going to draw sky on top of the terrain in a filled-in circle. And I'm going to use Bresenham's circle algorithm to do this. I've just lifted this direct from Wikipedia. They've even got it in C. But I have modified it slightly. Instead of using putpixel to draw a circle outline, I'm using these coordinates to create a line, essentially a scan line horizontally across the screen, to draw a filled-in circle. And just because I like using them in my videos, here's a lambda function which creates the filled-in Bresenham circle. It just takes an x-coordinate, a y-coordinate and a radius, all in integers, and this is in world space, so this is affecting the bitmap image that represents the terrain. And it is literally a cut and paste from Wikipedia with a small modification for drawing lines. So now I can create a crater, that's difficult to say, by drawing a circle of sky located around the world x and world y coordinates that came in as part of our boom function and specifying the blast radius. So let's take a look. And that works very nicely indeed. I mean, I can sort of create explosions within the terrain, which probably wouldn't be normal, but I can etch away at the terrain, it creates debris, very nice. One thing to try is now of course we can place an object and create an explosion underneath it, and the object reacts to the terrain. So this is a very dynamic terrain and physics engine. In much the same way that we've defined the debris in the dummy object, I'm now going to define a missile. And I've created a model here which is a little bit more sophisticated than just a rectangle or a circle, so it's got multiple points. I'm going to update my onUserUpdate function that when the user right-clicks on the mouse, it adds a missile to the queue to be processed. And again, we're exploiting polymorphism just to take care of everything for us. I'm not specifically checking what any object is at any time. I don't want my missiles to bounce. In fact, I want them to call the boom function and explode when they contact the terrain. So I know they've contacted the terrain because of my collision routine. And if I set the bounce before death number to 1, that will set the dead flag on the first contact. So I can do something under these conditions. And I'm going to create a function called bounceDeathAction, which is a function of my cPhysics object, which I'm going to use to get information about what to do when the object dies. And I need to add this to my base physics object as a pure virtual method, which also means I need to update it in all of my subclasses. So for debris, it does nothing. In this case, returning 0 means you've bounced and died, just do nothing, disappear. And we do the same for the dummy object. However, for the missile, I'm going to get it to return 20, which means please call the boom function with a radius of 20. So going back to where we're checking for this, once the unit has been declared as dead, because it's bounced enough times, we look at the response of the bounce death action, and if it's greater than 0, call the boom function at that location.
This approach allows us to create something like a grenade, which can bounce several times before exploding.
Let's take a look. And so if I right click, we can see a missile falls, and when it contacts the ground, it causes a big explosion. Let's just put some objects in here too, and drop bombs on them, and we can see they get kicked around all over the place. Very nice. Let's now finally add our worm class. Except the worm class is going to load up a type of OLC sprite. I'm not going to use the wireframe model to represent the worm. And so in the draw routine, I'm just calling the drawPartialSprite function of the console game engine. And of course, the units can bounce around, but I don't want them to die. Unlike the other objects that we've derived, I don't need a factory function because I'm just simply loading up the sprite. Let's change what happens now when the user right-clicks. So instead of creating a new dummy, we're going to create an object of type worm. The object's location will be wherever we've clicked. I don't need this. Let's take a look. So by pressing the middle mouse button, I can now drop units onto the map, which are sprites, and you can see they sit nicely on top of the surface of the terrain. I've increased the damping factor of the sprites because I don't want them to be uncontrollably bouncing all over the map. but they do have a small response. And it's fine-tuning like this that takes a bit of time. Let's drop some bombs on these guys. Perfect.
And so hopefully now you can see the advantages of using a polymorphic object-oriented system for handling your game engines. It just makes coding simpler and easier. So far, all we've created is a rudimentary physics simulation and some basic graphics. We'll look in the next part of this series at turning it into more of a game. However, I've uploaded the source code for this part already so you can start to study it. That's available on the GitHub. If you've liked this video, big thumbs up please. Don't forget to have a look at the Discord server, it's very active and there's a lot of people on there offering a lot of help. Have a think about subscribing and I'll see you next time. Take care.